Hello, Kia. Hello, Vola. Hello, Sarah. Hello,
Hello,
Boston.
Professor.
And Lina will join maybe for the last 15 minutes because he's in the lab doing experiment. So I believe I'm much better prepared for Fridays than for Tuesdays because there is a sequence of meetings in the day. But let me share the plan verbally, and then we'll go to slides and a little exercise at the end that I believe everyone will enjoy very much. So we are in the computational chemistry class, and by now you are certified experts in many important things. So you know practically how to build models or how to download them from databases, and you are aware of the fundamental backgrounds for separating nuclear and electronic degrees of freedom. And you are aware of treating nuclear degrees of freedom with a concept of potential energy surfaces. Thank you everyone for sending the slides. I will show something that I did myself years before, but I will probably use some of your slides for the next year. And as a little feedback to the last little homework with definition of potential energy surfaces, everyone did perfectly. No grade lowering. Grades are excellent. But a suggestion that the definitions that everyone provided in this little slide looks like empirical. So following how things appear for us. And no one mentioned that potential energy surface is summation of Coulombic forces, repulsion forces, plus eigenenergies of electronic state, which is kind of self-evident in this course, but later when you will be writing papers or thesis, you may impress your readers by mentioning this fact. So by now, I will chat more and discuss and show slides on potential energy surfaces, but we will need to get some ideas behind the geometry optimization that you already did show on Friday. In Avogadro, when you click the button energy with arrow down for energy minimization, and for broomstick in Gauss View, and there will be more advanced thing in the Gauss View that I'll show sooner. So how do we interpret this movie when interatomic distances find their best values? So I will chat about it, offer an algorithm which can be programmed into computer language to make a code for geometry optimization. And since we are not programmers, we are not going to code anything, but we will do, how to say, human programming. We will write this code, and then each of us will try to follow it, pretending that each of us is a little computer that tries to follow the code. And since we do need to make this code quickly converging, instead of actual complicated multidimensional molecule, we will take a simplified example that corresponds just to diatomic molecule, which has only one nuclear degree of freedom, the distance between two atoms. And each of us will be acting like a little computer. The homework, which will be due for Friday, will include repeating similar exercise with slightly different initial conditions. So, and before I go into the showing and slides, I want to quickly share one Google Docs with everyone. So the Google Docs that I will share in a second will be a protocol of a computer or a human following this little algorithm. So I did share it by the Zoom chat line. I'll probably send it to the email, and during the last 15 minutes of the class, we will collectively fill this table. Right now it looks boring, but after things that I'm going to explain, I make a bet. All of you will like it very much. You will consider it as fun.
So we need to calculate those values?
Yes, but not immediately. Just wait until we will come to the last 15 minutes of the class.
Okay.
Okay, thank you. And I'm starting to share screen. And going to the slide for today. So I will share the slides with everyone after the class, and I will rename it into the lecture 8 because number 7 were your presentations. So here is the table that I will encourage and invite everyone to fill at home.
Okay.
And the very similar table with just slightly different values here and there, we will do right in class. And I suggest we will do maybe one person fills one line or one person fills one cell and then goes forward. And through this Google Docs, it should be easy and possible. So the class combines theory, skills, and scientific communications. We are getting through background, build atomic models that you already know how to do it, and then we will launch correct software on correct hardware to predict properties of materials and compare them with experimental properties of molecules. And last thing before we went to the presentations were this table with chopping electronic and nuclear degrees of freedom and treating electronic degrees of freedom on one hand and nuclear degree of freedom on the other hand. And we came back through Ehrenfest theorem back to equation that looks like Newton equation of motion, but here the force is computed with taking into account quantum contribution from nuclear degrees of freedom. So what does it mean practically? It means we, all of you, are bosses, masters, and wizards of space and time for ions. So with these equations, you are able, or you will be able, to predict the position of a given ion at a given time. And this idea of being able to predict the future in a narrow sense for several small objects was a big inspiring idea for world science effort in about beginning of the 19th century, when this Newton's mechanic was progressed forward, and it was an idea that one can predict the future for anything, at least for small objects. Later on, one found that there are some objective difficulties, but if we know position and momentum at a given time, we can progress it forward. In order to practice this procedure of predicting position as function of time, we do need forces. Right? And the forces.
Professor, P is momentum and R is position, right? There.
Yes, yes, correct.
Okay.
So we need forces which are a gradient of energy over position, right? And if we do know potential energy surface, then by taking derivative over position of potential energy surface, one can predict the change of momentum. And change of momentum will allow to predict change of the position. But in order to practice such predictions, we do need potential energy surface at each value of interatomic distance. So we need to recompute value of total energy at each interatomic distance, or we need a pre-made table of forces for each interatomic distance. And this table of forces is often referred as force field methods, where one predicts through quantum calculation or through empirical fitting the interatomic forces at each specific distance, and then utilizes it for molecular mechanics or molecular dynamics. Yeah, I think it's just conversion between Hamiltonian and Newton equation of motion. So if we accept the let me write it over, otherwise it will be boring for everyone. So if I plug one equation into another, so I did apply a second derivative to the top equation, and then here I do have, instead of momentum, I have a derivative of momentum, and instead of derivative of momentum, I can plug in the force. Right? So it is same as Newton equation of motion. Now, if I want to use this equation to predict future, please give me suggestions. How do you solve Newton equation of motion? If you do high school physics or college physics, just basic approach. If there is a specific, like instead of force, it can be, let's say, like it can be proportional to distance with minus sign, or it can be some other function of position. But generally, please give comments. How would you solve this equation by pen and paper?
Integrate.
Right? Thank you, Boston. Are there any questions, or does everyone agree with this statement? Do I need to give additional comment? Just show yes or no. I do not mind.
Yes.
Yes mean give comment. So one does need to obtain position as function of time, right? And here this equation includes second derivative. The procedure inverse opposite to differentiation is integration. So if we apply integral over time once, and if we apply twice, then this equation has to convert into just r of t equals to something. And it will be a way to predict future. Make sense? So by putting these colorful symbols of integration, it is what Boston suggested us to integrate this equation. So the force is derivative of potential energy surface over position of ion. So in the next slide, I just apply the first integral to left and right part of this Newton equation. And just because personally I'm lazy, I stopped placing this angular brackets. So if we need to report it in public, we will say that we understand that instead of classical positions of ions, we are dealing with expectation value of nuclear wave function. But in practice, it's similar, it's easier to deal just with this R variable. And if there are many ions, there will be indices. Okay. There is a little difficulty, which is not big, but objective. We do not know predominantly what is this potential energy surface. It can be anything. And we want to find a way to solve this equation numerically instead of integrating. So there is a way to limit our power from predicting to infinite time towards predicting only a small increment of time. And if you look for small increment of time, then some tricks can be done with integration to make it solvable in any case. And what we are going to do will be just solution in finite differences. So let me write a couple of equations. They are available on in the next slide, but it will be much better for our discussion to have them written as we go. So if we integrate the equation from the previous line, the upon integration of second derivative, we are getting the first derivative plus constant, right? By the rules of integration in calculus, right? By integrating the gradient of potential energy surface, we are just multiplying this stuff by time increment, because for variable t, for time variable, all of this thing can be considered as a constant. So it's same as integration of a constant. So will be this minus d du dr times t. Or if we want to be really, really meticulous from 0 to t1, one can put here t1 0. What would happen if we apply the, and I apologize if I repeat some baby steps, but it's better if we see the steps, you will feel much more confident and comfortable. What if we apply integration once again?
Then you will get only r and left side r, and in right. Oh,
right. We apply integration over time,
okay.
and then the derivative over time will convert into r, right?
Yes.
What would happen to the constant?
Constant will be 0.
But no.
You'll get a t.
A t. Constant t.
Correct. Constant times t. Or if I want to be really meticulous, it will be, okay, let's put it t by now, equals. And what would happen if I integrate this gradient times t? If I integrate it over time? Like, what is integral of
power 2 for the t? T power 2?
Over 2, yep.
Over 2, correct. So t power 2 over 2, and then keep here minus du over dr.
Yeah.
Right? So I suggest just a little thing for comfort. I keep r on one side, and we always add a constant after each integration. Maybe here will be constant 1, here will be constant 2. So our position as function of t will be, now I put everything else on the right side. So constant 2, constant 1 times t, plus, or I can keep the sign here, minus gradient u d r times t squared over 2, right? So what if I'm looking for transition from time 1 to time 2 in such way that their difference, t2 minus t1, will be something really small that we will symbolize by symbol delta t. So duplicate slide. So just erase this unnecessary stuff. Then this specifics about time, we'll say that r of t1 plus delta t. Then I'm skipping little details, but one can fix what should be constant C1 and C2 by considering time increment equals 0. So if time increment equals 0, then only constant C2 remains, which shows that it should be just position at time 1. If one continues, if one takes derivative, considers derivative at time equals 0, one will find that the constant C2 will be velocity at time 1. One multiplied by delta t. And the last term, most important one, will be the gradient of the potential energy surface that depends on r at time 1, close bracket, multiplied by delta t squared over 2. Any questions or comments to this little equation? Okay, so now you can teach college physics. And question?
Yes. Why did you replace minus C2 with RT and C1? I don't really understand what happened in your last line.
Okay. I'm happy to answer. So if T equals T1, so we just plug T1 into the first equation. Then we will obtain R of T1 equals unknown constant C2. No. Sorry, I apologize. No, I do not apologize. Everything is good. So unknown C2 minus C1 multiplied by T1 minus T1. So I plugged here the T equals T1. Minus this gradient dr, and here I placed T1 minus T1 squared divided by 2. So this is 0, right? Subtraction of the number from itself. Therefore, the second term will be 0. T1 minus T1 is 0.
Mhm.
Square of this is 0, so the last term is also 0.
Okay.
From here, we see that minus T1 must be equal to R of T1. Minus T2 equals R of T1.
Okay.
There is the same trick if we take derivative of this star equation, and if you take derivative over time and then once again plug in t equals t1, then we will solve for minus c1 equals ddt time derivative taken at time 1. I'm just lazy to show it, but if you want, I can show it. Make sense? Okay. So how do I interpret it? So it is the same equation. If I know the position at time, let's use the same indices, time 1, then the position at time which is incremented, which is moved forward compared to time 1, will be, you'll consider value of position at the previous time step times velocity times increment of time. So this momentum divided by mass is velocity, right? Minus the term that is quadratic in time. So if in the high school physics and introductory college physics, the first example where it is practiced is the free acceleration fall of mass in the gravity, right? So now, how can we chop this equation? And right now, to practice this equation, I do not need the complete knowledge of this u function. I need only the specific values at each new time step. So my goal will be to chop this equation onto a more algorithmic sequence of operations. So to define forces as gradient, to formulate these forces in finite differences, means in terms of the increment of time. Second derivative, result of the second integration, what we just did. And then, here, the change in the position, which means position at time plus delta t minus position at time t will be this momentum or mass times delta t minus gradient over gradient of potential in the surface times delta t squared over 2. So by practicing this equation in finite differences, we will be able to predict how much position, how much interatomic distance will change if we look forward in time for the time increment delta t. So force is gradient of the potential in the surface And if we want to recast this definition of force in finite differences, which means take the definition of the derivative. So the definition of derivative is the limit of increments, increment of force, increment of the potential energy surface to the increment of position, which means u at next step, or we can take it. Let me be consistent. First, u of r of t plus delta t minus u of r of t divide by r of t plus delta t minus r of t, right? No one objects this definition, okay? And if you are speaking with mathematicians, there should be a symbol of limit here. Delta t goes to 0. If we say that t is our step number I, and t plus delta t is our step I plus 1, if we go forward in steps, not continuously as mathematicians, but discrete as computers, then this definition is reformulated this way. And this definition of force, this gradient in finite differences, can be plugged into our equations that we use to predict future. How to predict position at time delta t if we knew t plus delta t, if we knew position and momentum at previous time step. Okay. So we are almost done, and we are almost ready to go to practical thing. So here is how I would do my own homework by copy pasting this example image from the online and from the textbook. So here is the z-axis is potential energy surface, and it has like global minimum, local, several local minima, the maxima, inflection points, saddle points, like transition state, which is important for catalytic reactions. And right now, we are going to, so these potential energy surfaces are especially important if one describes bond breaking, like one local minimum is reactant. Before reaction goes, the global minimum can be the product after some bond breaks and forms. But since we want to be very simple, just as an example, we will consider optimization in the vicinity of the global minimum, where most potential energy surfaces look as a square function, as a quadratic. So we are having two options. So one option and I tell that it is not the best one, is to scan through all possible interatomic distances, compute potential energy surface for any possible distances, which means reconstruct potential energy surface, and then practice sorting. Just put it into the Excel table and find which value will give the minimum here. And if it is a consistent table, at the we will see in the same line which interatomic distances give the right position. So one doesn't need anything except Excel. This idea is correct, but very time-consuming. And I'm going to show an example. So if you have diatomic molecule, there is only 1 degree of freedom, and consider we will chop the interatomic distances on only, let's say, 10 discrete points. Then this potential energy surface will be represented by 10 points, and finding minimum out of them is really easy. If you have triatomic molecule, number of degrees of freedom is 3n-6, because one subtract 3 rotations and 3 translations. So 9 minus 3 minus 3 will be 3. So since motions in several directions are independent, one will would need 1,000 points, right? Because they're independent and one needs to multiply. If there are 4 atoms, 3n-6 will be 6. So one will need 1,000,000 of grid points that we compute for each point and then plug it into Excel, which is 1,000,000 is still doable. But if you go to like methanol, how many atoms? 3 plus 1, 4, 4 plus 1, 5, 5 plus 1, 6. So 6 atoms, it should be like 3n-6. 3.
Professor,
Yes?
does the formula apply to diatomic? Does the degree of freedom formula apply to 2 atoms? Because if you put n equals 2 in the formula, it's not going to give me 1.
No, it is not applicable.
Why?
Why diatomic atom is a special case? Because I can explain.
Okay.
Thank you for bringing up this question. So if you have 2 atoms, here's one here. It's not a smiling person, I'm trying to draw a sphere. So it's like a dumbbell object. It can rotate by changing angle in this direction.
Okay.
It can rotate by rotating in this direction, right?
Yeah.
But rotation of the molecule along the axis containing these 2 ions is not possible, it's not defined.
Okay.
Because size of the atom is not known, or because it is symmetric, and by rotating this dumbbell along its axis doesn't bring anything.
Okay. Yeah.
Therefore, we do not count this degree of freedom and do not apply DOF equation. We do not apply DOF equation to the diatomic.
Okay. Thank you.
Oh, my pleasure. Thank you for the question. I'm really happy. So 3 times 6 minus 6 will be 18 minus 6, 12, which means what's the right word for 10 to the 12th? Like terabytes for information. So it's like tera something, 10 to the 12th, tera number of the elements in the potential energy surface. So a terabyte T, so so we need to in order to practice this methodology to quite small methanol molecule, we need to fill the terabyte disk completely. And if we have something bigger, we will not be able to do chemistry. So it's not wrong, but very ineffective algorithm. Instead, we can try a different algorithm. We will select arbitrary initial interatomic distances as we draw with the chemical drawing software. Then compute where the gradient is shown, where the force is directed, and make one step in this direction. Then in new point, we recompute force and make another step in the direction where force is pointing. So instead of looking over all points of the potential energy surface, we look only on a one line that will be always directing toward the minimum. And here I'm going to introduce how it works. This browsing in the space of position. So at some step we have position, then we suppose we have either force field or electronic software that computes electronic problem and gives value of potential energy surface only for this position once. So we do not need terabytes, we just do it once. And then to start we need 2 points, but then we subtract the value of energy at the previous and next point and compute gradient. And as soon as this gradient is known, we assume that we know the time increment, and we combine these two things in one equation and compute what will be the next delta R. So in which direction and for how far we should travel to eventually reach the minimum. Any objections or questions? Okay. Oh, I see suggestions to explain several slides. Yeah, let me finish in case some of you need to depart in time, and then I'll answer. I see questions in the chat line. Now, what is my next goal? Thank you for the patience. I understand that it may be not clear. So these equations and finding differences need to be translated into the protocol, into the algorithm to be followed by a computer. So I introduced a dictionary. So this dictionary is used in order to communicate between regular people and professional programmers. Suppose I do not know any programming language. Suppose I have enough money to hire a programmer. How can I explain which problem my programmer needs to solve? So these flowchart diagrams were originally designed to communicate between regular people and programmer, and it is independent on the programming language. It's just to communicate idea and follow sequential set of operations. And typical notations are this symbol of disk is for data, right? because in the computers we used to use hard drives. Now we use SSD, but solid state, but disk as a symbol of data. Arrow shows the transfer of data. Rectangular corresponds to math, and the diamond corresponds to forking, where depending on some condition, one can process data in one or another way. So what I'm going to do is to combine our finite difference solution of the Newton equation for browsing potential energy surface and this language. So I'm going to draw the algorithm for solving Newtonian equation. And instead of drawing in front of you, I'll just show already pre-made algorithm. So you recognize the steps that we did discuss. So one takes the gradient, multiplies it by delta t squared, and computes increment of the interatomic position. Then new interatomic position is computed by old interatomic position plus this increment. And then as soon as we know the new incremented position, we can use it to compute the new value of energy. And then we repeat this procedure again and again, hoping that through this algorithm, we will approach the minimum. Right? So I know that probably today I will be slightly over time, but let me tell a joke. It's not a new joke for me. I tell it every year, but maybe you appreciate it. So a company where several programmers are working, and one day one programmer didn't came to the job. He missed the day. He missed the second day, and then the boss sends a team to his house, to his apartment, to check whether the person is okay, why he's not answering phone calls and not coming to the work. And the team comes to his apartment and sees that the person is like blue, cold, shaking, sitting in the bathtub, holding the shampoo bottle, and reads, apply to hair, rinse, repeat. So if you're laughing out of this joke, then you understand why we need this diamond. So we need to make interruption so that we do not repeat this procedure forever, right? And we will stop it. We will this procedure if the subtraction of the potential energy surface at step n+1 and potential energy surface at Tn, which we define as delta U. So if this delta U will become smaller than predominantly defined tolerance limit. So before we start procedure, we need to agree that there is a precision tolerance limit, like 10 to the 2, like 0.01 in units of energy. And if we reach this level of precision, we should stop, no matter where we are. So we need just some rigorous definition. What is the criterion of success? And if this criterion of success is matched, then we report the last value of the interatomic position is optimal, is the best one, and last value of the potential is optimal, the best one value of the total energy. We can do another interruption. If a system gets stuck browsing through several local minima, we do not want our program to work infinitely long, and we can add another interruption. If it takes more than 10 steps or more than 1,000 steps, then we should stop the program anyway and tell that it doesn't work, it was a failure. Okay, so I suggest we practice this equation for this algorithm for a very, very simple example where potential energy surface is equals r squared. So just a parabola. And the answer that the u opt will be 0 and r opt will be 0, right? We all know what will be the answer. But suppose that I am a stupid computer who doesn't know this human knowledge, that the minimum of this function is at point 0. Suppose I'm starting somewhere aside from 0, and now I need to find this point of minimum by an algorithm, by some rigorously defined set of steps. So to be specific, I want to set up the initial value of position. I need to find the setup tolerance limit. And the first step needs to be done arbitrarily because we need two points to compute the gradient. And also I set up time step equals square root of 2. I just set it up because square root of 2 squared divided by 2 will be 1, just to simplify our life. And this parameter gamma, I would say it corresponds to damping, to avoid accumulation of momentum, to avoid jumping over the minimum. For example, if our time step and increment are very big, we can accelerate so much so that we will jump over the minimum. And we need some damping and go forward a little bit shorter distance than is actually predicted. So I suggest we all go to the Google Docs and start filling this document. I will do the first line, and then each of us will continue. And I promise it will be not hard, and it will help to complete the homework really efficiently. Let me check if I can. How do we? Maybe this way. So U, value of energy at -5. I take 5 squared will be 25. Right? Then for the next step here, I cannot do anything because I do not have the first step. Now.
So now it's 5.
Okay.
24.
So I do step number 1. Step number 1. And just by taking this value that increment is postulated as +1, -5 + 1 equals -4. Now I have 2 points, and from here I can go further. So potential energy, so -4 squared will be 16, right? Now I subtract these two numbers. So I subtract 16 minus 25, which will be 9, correct? Now I compute the gradient. 60 minus 25 will be minus. Thank you, Kia. Now I compute minus 9 divided by 1.
9.
Yes, will be 9. Now we agree that our delta t is square root of 2. Now delta t squared over 2 will be 1. And now I compute this delta r as minus, then this gamma is 0.3. Now I put this, the gradient will be 9, and then delta t squared over 2 will be 1.
Shouldn't be it negative?
So he already deducted, means
No. I put negative times negative is positive.
Professor, for there is an equation. In equation there is a negative sign. Maybe Sarah is talking about that.
Please repeat.
Yeah.
In equation there is a negative sign. Before gamma there is
I
a
got
negative sign there.
Yes, but this negative is attributed to the gradient. I should put gamma times minus gradient.
Okay.
Gamma times.
Yeah, I got.
Okay.
Okay.
Yes. Sir.
So
0.2.
I'll do maybe few cells more, and then we'll try one after another. So step number 2, the new position will be minus 4, which was previous position, plus 0.27. I take what we computed at the end of the line. So minus 4 plus 0.27 will be minus 3.73, right?
Yes.
Okay. And from now on, it becomes too complicated for me. So I need volunteers to help me and continue.
So we need to.
So please connect. Do not dictate me. Please connect to this Google Doc that I did.
Okay.
And try.
How to connect it? Let me see.
It's 13.91.
Okay, someone should type the number.
Professor, if I want to fill up this one, how to do that?
I do not know. I'm not big expert in this Google Docs. So who typed this 13.91?
13.
That's me.
Okay, so Boston, let's maybe you continue this line, and then we'll take one line per person.
Okay.
So what will be delta U? Current minus previous.
Minus 2.08.
Looks right for me. Boston, do you agree?
Sorry, yeah, I'm trying to manage the thing.
So for the gradient, you need to divide the number from last cell over increment, over the last increment, which was 0.27.
Okay.
15.73.
Thank you, Sarah. And I think it should be positive because we again have negative energy, positive increment, and
What'd she say it was?
No, it's 7.7.
I was gonna say,
7 point there 2.08 divided by 0.27 equal to
7.7. Yeah.
7.7.
yeah, that's what I got as well.
and do not be super precise. We just need general time.
Okay, 7.7. Then it's square 2. Then obviously it would be 1.
1.
Then 0.36. Then 7.7 into 1. It's 2.31. Del R 2.31.
Yeah.
Last del R is equal to 2.31.
And you can just pull
Yeah.
the edge of the. Oh, edge. I think I can do it. Yeah, good. Very good. So who is next?
I can.
Sarah, would you like to do the next line?
Yes.
Okay.
How to.
With Google.
I think one can select this T text box and just click, and or if you already created to move it. Yes. Yes.
Three. Then it should be -3 plus
Plus 2.3.
2.3 is equals to
It's not -3. It was -3.73, right?
Yes, minus 3.73.
oh yeah 73. Calculate it.
Minus 1.43.
Mhm.
Just right. Minus 1.43. Sarah. Minus 1.43.
Okay.
1.43 square is 2.04.
2.04.
Yes.
Mhm.
Then del U.
Oops.
What is del U?
Delta U.
And now we need to subtract this new minus 4.
2.04. 2.04 minus
2.04 minus
13.91.
What?
2.04 minus 13.91.
Minus.
That's 19.89.
Minus 13.9.
13.91.
Mhm.
2.04 minus 13.91 is equal to minus 11.87. Okay. Then this one will be divided by del R. Del R is previous one. So del R minus 11.87 divided by 2.3 minus 5.16.
Minus
5.16.
16.
Yes.
Are you sure about the sign?
Yeah, I'm sure.
Uh,
Just a minute. Okay. No, it's positive because
correct.
yeah, 5.16.
Good.
Okay.
Then it's square 2, same. Square 2. Then 1. And del R will be 1.55.
1.55.
Yes. Okay.
Okay. Who is typing next?
Me.
Okay. Yeah,
Oh,
thank you, Sarah. Okay.
why cursor is not there?
Just type space.
Space. Okay.
Space just to move across.
Oh. So it will be minus 1.43 plus 2.3, right?
Plus 1.55.
Okay. You are helping me. Thank you. Plus 1.55.
And
Then
remove this 2.3.
remove.
You have 2.3.
There.
No,
One-
no, no. Wait.
Okay.
Oh,
Sorry, it's 1.55. I
No.
did mistake. Yes. Yep. Plus 1.55. Then it would be minus 1.43 plus 1.55. 0.12.
1, 2, yeah.
So let's make a little stop, but we will continue in a second. Please join me in looking on the second column. So we started from -5, then we went to -4, then it was -3.7,
Yes.
then -1.43, and now we
Positive.
got to positive, and we are
Yes.
really close to 0, right?
Yes. Yes.
So we are
Mhm.
approaching in the right direction, and you see that we jumped over 0 to the opposite side.
Okay.
Okay, let's continue.
Then 0.0144, the previous one, and minus 2.04, right?
Therefore,
Zero.
yeah,
Yes. So
that's
there,
minus
0.04.
2.0.
Okay, just a minute. Minus 2.04. It should be equal to minus 2.03. Okay. So then after that, again space 2.03 divided by del R. That means previous one, 1.55. 1.55. It should be 1.31. 1.31. Okay. Then SQ T square and 2. Then S1. Then there go it's 0.3 into 1.31 into 1. Oh, 1. What happened? Okay, I can understand. 1.31 into
0.39.
3.393.
No, 0.39.
0.39.
Oh, I did mistake. 1.31 into 0.3. Yes,
0.39.
3
9.
is. So I need to turn it there. Now it's good.
So,
Yeah.
okay. And who is next? Vola?
Yeah.
So, yeah, good. Let's make a quick stop and let me attract your attention. Let's look on the column number 4 from the top to the bottom. So first we had -9, then -2, then -11, -2, and now for the first time in our life we have it positive. The sign flips. So before we were going from negative side, negative, negative, and now we jumped over the minimum to the positive. And now the system self-corrects. It recognizes, this algorithm recognizes that we went too far and we need to return. So this delta U changes sign, which means we need to return back, and we went, like we were running so fast that we missed the target. We need to return back. Make sense? So please continue.
Okay.
And what is the sign?
Oh, negative.
Yes. So the force in the column 5, for the first time, we get a negative force, right?
Yeah.
Minus.
0.19.
And the
Minus,
sign should be
right?
negative. And the sign should be negative, right?
Negative.
Yeah, negative.
And if we go to the, thank you, Lola. If we, I'll do just quickly. If you go to the step 6, then the next will be the previous value of 0.30 minus 0.19 will be
0.32.
32. So we are not, the algorithm is not done. We didn't reach the tolerance limit, and we didn't reach the count of 10 steps, right? But you see that it was negative approaching 0. Then we went over the limit, and now the algorithm suggests us to return back. And if you continue, it will return closer to result, to the result that we understand as humans. And I believe that everyone got understanding how the algorithm is working. And I believe you convinced that by programming through this algorithm and using multidimensional potential energy surfaces, it will be working still as quick, so one can find optimal place in like 10 or 100 steps, even for very complicated potential energy surfaces. This is oversimplified way of describing potential energy surfaces and optimization algorithm, but it shows as an illustration what is going on. So please try to use the same algorithm with slightly different initial position and slightly different tolerance limit that I will show. I will send by the email. And with this, let me announce the end of the lecture 8. So thank you much for your patience and staying over the time limit substantially. I hope that you enjoyed it. And you can, if you select industry or research career, you will just run optimization algorithms for your problems. If you select teaching career, you can offer this little exercise to your students in the future. Well, I'm done. Lecture is over. Everyone is welcome to disconnect. And if there are additional questions, I'll stay here to answer them, but formal part is done.
Have a good night, everyone.
Good night, Boston.
Thank you, Professor. Good night, everyone.
Good night, Sarah.
Professor.
Yes.
You mentioned something about an assignment. I'm not sure of what.
Skip it. There will be. I'll send an email explaining what everyone should do now.
Okay, but then last week Friday you also made mention of an assignment for Tuesday, and I don't know. I had no idea.
Don't worry. It's suppose it is done for you.
Okay.
So if you're really interested, an assignment was. Let me show screen once again. To draw a slide like this, okay, with maybe a little bit more explanation. So explain what is potential energy surface. But since we are over this material, there is no reason to look back into past material. You'll have chance to do next homeworks.
Okay, thank you.
Oh, thank you.
Good night.
Good night.
Professor, last time I sent you email that actually most of the time I review your lecture and Professor Winji's lecture during the weekend. So then I found that a few things I'm not able to understand. So
So it's, should I go to the slides? You are
Yes,
26, 31, 33.
40.
Yeah, what we do it? So 26. So
Lecture 6.
26,
From lecture 6, yes, 26.
26. So this gamma, which we take like 0.3, just means
So
that
this one from lecture 6, Professor.
oh, previous lecture. Sorry. Okay. So tell me what is not clear.
This one 26, yes. Professor, there in the equation,
Which one?
the first one. From first one, how you able to get the second one? Like,
So these equations are not from this class. I refer to the something that comes from quantum mechanics or physical chemistry. If you were not taking these classes, it will take noticeable time to get through them. I can quickly summarize what these equations mean, but it definitely will take like longer than a couple of minutes. It's like maybe an hour.
okay, just explain.
But let me quickly comment. So if you see this image,
Yes.
so the thing that I just highlighted is potential energy surface, harmonic potential energy surface, parabola, right?
Okay. Yeah.
And the thing that I'm highlighting with green
Yeah.
are quantum eigenstates. And the equation 1 is for this quantum eigenstates,
Okay.
which I believe you will take some quantum mechanics or physical chemistry in your studies, and you will see both equations and images. So this minus variable squared shows that as we go to infinity, it gets very small, and this h is a polynomial, is like variable squared minus 1, for example, or just psi, or just 1. So it's different polynomials of this independent variable. And to be consistent, it should be the same variable here and there. Okay, so those are eigenstates that do not change over time. And here is example of time-dependent solution, which shows how the wave function changes over time. So it's also has this if one takes this integral, that it also takes an effort, one will obtain that this equation will be looking like e to the minus x squared, which shows that it is localized, minus x times p times imaginary unit, and imaginary unit is square root of -1. So this function will look like quickly oscillating stuff that is 0 before and after. And this quickly oscillating stuff corresponds to wave function that quickly moves through space.
So at the end of it's at the end of the time, it's actually it's going to be 0.
So the axis here is position
Yes.
is
Okay.
whatever we call x or rx, and time shows how this little fringes, how they will change with time, and this solution will show motion forward and backwards. So it will be, if you look into the parabola,
Mm-hmm.
it is motion in the parabolic function. It will show that this wave function will move forward and backward repeatedly, forward and backward, which corresponds to just oscillations of interatomic bond.
Okay.
Enough?
Yeah, it's
Okay.
enough. And then this equation, the below, psi bracket r t, yes. So from where you get this one, and what's the physical meaning of that?
Okay, so if you accept the last image I did draw for you,
Yes.
then you see that this thin Gaussian profile, which goes to 0 at plus and minus infinity. This function looks very much like something very tall and very thin.
Hmm.
And very tall and very thin function is called delta function,
Yeah.
centered at the expectation value of position. So we are telling that we are not going to bother about the width of this function. We will assume that it is 0 width, and we just focus on that it is centered on the expectation value of the position.
Okay. Yep. Okay.
Should we go to 31?
Yes. Yes. Yeah. Okay. Now the previous that equation you just explained. So you use that equation here, right?
Let me go one slide before.
Okay.
So slide 31 is just implementation of this Heisenberg equation of motion.
Okay. Heisenberg equation of motion.
Mm-hmm. So I plug in R instead of A.
R is the position. Okay.
Yes. And A is arbitrary operator that we consider in general. And H is total energy. So if you look into online for Heisenberg equation of motion, you'll see both words and equations. And I'm at the fall semester. I'm teaching undergraduate quantum mechanics, and there is a lecture where I speak about this equation for about an hour.
Okay, it's on the online. It's
Yes.
It's already posted in YouTube, right?
Mm-hmm.
Okay. Is it possible, Professor? Could you please send me the link? Or
oh yes. If I do not do it within like 5 minutes, please send me a reminder.
Okay, I will. I will.
Thank you. So next 33.
Yes, that's it. I think it's real. It's related to the 31. Totally.
So from 31, yes, we through some math we obtained 33. Right.
Okay.
So next 48.
Okay. The same thing. From 38, we get this equation. There, partial divided by partial t, it's derivative of position. Then we get this one. After that, for ions moment p, so we get this one. So how can we get this one? This.
Which one? This one or this one?
This one. Yes, with p.
So
second derivative of the first equation, right? There is 3 equations. The above one, then second one, then third one. So it's when you derive when you did the second derivative of that second equation, then after that you get the third one, right? Right or wrong? Am I right?
Let me give notations. So
Okay.
let's call this one number 1.
Yes.
This one
It's
number 2.
2.
This one number 3.
Yeah.
And this one number 4.
Okay, it's a totally different thing.
So by plugging number 3 into number 2, we will obtain number 4.
Okay, the equation 3 is totally different from, okay, it's the
Yes, so your question, where did we take equation 3?
Yes, from where we get this equation 3? My
Yes,
question.
yes. I've got the question and I'm going to answer. Just give me a second. So we are going to practice Heisenberg equation of motion.
Okay.
But now instead of A, we will plug in P. So here is this. Here is the P,
yeah,
and here is the total energy. T plus U is H, Hamiltonian. And then there is a rule that since T kinetic energy is P squared, there is a rule that a variable in power m and the same variable in power n, commutation is always 0. Therefore, P comma T is 0, and therefore we exclude T from here, and we compute only the commutation of momentum and potential energy. And if we process this equation, it will give us time derivative of the momentum.
Okay.
So, okay.
Yeah. Now it's clear, I guess. Then I will check it again by myself. Okay. Thank you, Professor.
Okay. Yeah. Many thanks for your dedication to the class. I really appreciate you how seriously you take it.
Okay. Thank you, Professor. And I will send you the video for that one I made, but with obviously audio, so with voice.
Okay, thank you.
Because this week I'm a little bit busy. Maybe after the end of the weekend, this weekend I definitely I will send you.
That's okay.
Okay. Thank you, Professor. Good night.
Thank you. Good night, Kia.
See you tomorrow.
See you.
Bye.